Today. Okay, I'd like to welcome all of you to Einstein for Everyone. This is the first in a series of 3 courses that I've taught at UCLA and University of California, Channel Islands at their Osher Institutes. And these 3 courses together cover, begin to explore all of modern physics, at least the most important parts of modern physics. And the first course is about Einstein and his discoveries, and that's what we're starting today. The second course is about quantum mechanics and the microworld and elementary particles. And the third course is about the universe. So stars and galaxies and cosmology. So this is the first course, and we're going to learn about the discoveries of probably the most famous scientist in history, Albert Einstein. And the overview of the class is that we have 6 sessions. This is week 1. Today we'll talk about the highlights of his life. We will list his major discoveries and explore why these discoveries are important to all of us. We will then discuss his most famous equation, E equals mc squared. Throughout this course, we're not going to do a bunch of math. We're not going to derive the laws of physics or anything like that, but we will discuss the most important equations like E equals mc squared, and I will explain what they mean, why they're important, and we will leave it at that. We will end today with a discussion about Einstein's 2 wives and the odd circumstances of the award of his Nobel Prize. Next week, we'll talk about his discoveries that relate to atoms and elementary particles and wave behaviors. And this includes, for example, his discovery of the underlying mechanism for the photoelectric and the photovoltaic effect, and the understanding that we have of atoms, which Einstein made major contributions to, allows us to date relics, so like carbon-13, and we'll talk about how that works. Then the next week, we'll talk about his most famous theory, which is the special theory of relativity, and we'll see why Einstein said that moving clocks appear to us to be running slower than stationary clocks, and faster jets appear to be shorter but heavier than jets that are moving more slowly. In week 4, we're going to talk about his most profound theory, the theory that has changed physics to the largest extent, and that is his general theory of relativity. And it is pretty much all about gravity. And so we're going to find out why Einstein says that gravity is really geometry, it's not a force, and that the geometry of the universe is what controls the motion of all the objects that we think are being gravitationally attracted. In week 5, we're going to see some of the consequences of this theory, the impact of various physical behavior due to general relativity. So the bending of starlight, the change of the orbits of the planets, the change in the color of light due to gravity. We'll talk about the recent discovery of gravitational waves, which Einstein predicted about 100 years ago. And lastly, we will talk about his failed efforts to unify all of physics in one grand theory. Einstein set that as a major goal, and we're still pursuing that 50 years later, and we still haven't succeeded in unifying all the laws of physics in one comprehensive theory. So it was a great idea when Einstein had it, and it's still a great idea, but it's uh, still unsolved. And in the last week, we're going to talk about a little bit about cosmology. We're going to talk about stars and the behavior of stars, and in particular, how general relativity affects that. Then we'll talk about Einstein's discovery of the underlying mechanism which allows for the development of lasers. And then we will review all the material that we've covered in this course. So this would be a last opportunity for you to ask the questions that are still troubling you at that point. But you shouldn't wait for that. You should feel free to ask questions along the way whenever you wish. To ask a question, you need to have your audio on, and then I'll hear what your question. Okay, any questions so far about what the course is going to be about? Okay, so let's dive right in. And this is week one, and these are the topics we're going to cover today. So we will begin with the highlights of Einstein's early life. And probably the most remarkable thing that I can say about Einstein is that he was chosen by Time magazine to be the person of the 20th century. And of all the people that lived in the 20th century, of all the famous and the infamous people, of all the people that had dramatic impacts on society during the 20th century, they chose Einstein as the person that had the greatest impact on humanity. And it's really remarkable that a physicist would even be in the consideration for a topic like that. And they said of Einstein that he had the greatest mind and was the paramount icon of our age. I indicated earlier that he had won the Nobel Prize. He is the person of the century, probably the most famous scientist in the history of humanity. And so it would be easy to consider that Einstein probably had a blessed life. Everything came up roses for Einstein. What could be better than being the most famous scientist in history and the person of the century? And that idea turns out to be almost completely wrong, because in fact, no one in science has failed more often or been rejected by more people than was Albert Einstein. And so it's an interesting story as to how he managed to succeed despite this tremendous negative reaction that the Physics Society had to his ideas and to him in particular. So Einstein was a person who is very different from the norm. His biographer said he was always obsessed with the beauty and harmony of nature. This is a picture of Einstein, by the way, on the beach at Santa Barbara, and you can see from his attire that he really didn't fit in. Einstein declared that he was a lone wolf. By that, he meant that he didn't follow the pack. He set out in his own direction. And indeed, he really didn't care what anyone else thought about what he did. He was a complete free thinker. One might say he thought outside the box, but it probably would be more accurate to say that he never saw the box to begin with. He was completely absorbed by his own thoughts about what nature really meant. And he really had little to no concern about anybody else's opinion. He also had great difficulty in forging the kind of interpersonal relationships that all of us consider normal and important in our lives. So he certainly loved his children, but when they got sick, he couldn't deal with that. He would go into his office, close the door, and work on physics until the problem went away. So he had these odd personality quirks, and it wasn't diagnosed in his age because people didn't understand these mental issues. But in retrospect, some doctors have suggested that Einstein suffered from Asperger's syndrome, which is, I'm told, a mild form of autism. His biographer said of him that he cared passionately about humanity and sometimes even about individual people, but not too often. Well, to begin his biography, Einstein was born in 1879. He was born in the southwest of Germany in the city of Ulm. And his parents were Jewish, but not very observant. His family had apparently lived in that area for at least 2 centuries. And by that point, they considered themselves more German than Jewish. Of course, when the Nazis came to power, those issues changed dramatically. He was actually very slow to learn to speak. It's said that he didn't say anything of note until he was about 4 years old. And he seemed to be eternally absent-minded. So he was never paying attention in class. And he managed to get himself expelled from the 2nd grade for being inattentive and disrespectful of the teachers. You have to work pretty hard to get expelled from the 2nd grade, but he managed to accomplish that. And the headmaster told Albert's father that your son will never amount to anything. In retrospect, that sounds ridiculous, but at the time, this was a relatively common notion of the people that knew him. And indeed, it's remarkable how close this headmaster came to being absolutely correct. Einstein dropped out of high school in the middle of his sophomore year, and he then tried to get accepted into a less than top tier college in Switzerland, the Polytechnic Institute. It's more renowned now than it was in Einstein's day. And at the time Einstein applied for admission, the Polytechnic did not offer advanced degrees. So that made it less than a top-notch university in Europe. He indeed failed the entrance exam the first time around, and he had to study an additional year in Switzerland in a Swiss high school in order to gain admission the following year. He was not a diligent student. He didn't work on assignments that he considered below his intellectual stature or uninteresting to him. So he got some very poor grades, including an F in one physics class, a lab class, which he had no interest in. And he graduated number 5 out of a total of 6 students, so next to last. In addition to his low ranking, he was considered by his professors to be a very insolent student. And his math professor said that Einstein was a lazy dog. His math professor was named Minkowski, and Minkowski made a significant contribution to the mathematical description of Einstein's theory of special relativity. So along the way, Minkowski must have changed his attitude about Einstein. But at the time of his graduation, Einstein had both very low grades and the worst imaginable references. So none of his professors gave him a favorable reference, and in fact, the references were rather negative. So with poor grades and these horrendous references, Einstein was rejected for every position he applied to, from Norway to Italy. He applied to almost every university in Europe and was not even offered an interview for any of those posts. And he applied at every scientific institute in Europe. And again, he was not even offered an interview for any of those jobs. So he was rejected to the maximum possible extent by the entire scientific community of Europe. He did manage to earn a little money by tutoring, and he sustained himself primarily by money he received from more well-to-do relatives who wanted to keep him from becoming a homeless person living on the street. Without a job and with just this meager income, he was unable to settle down and marry the love of his life, Maleva Merrick, and start the family that they both wanted to start. And his parents rejected Maleva for various reasons that we'll discuss later. And she didn't come from the right part of Europe. She didn't come from the right religion and so forth. And that his parents demanded that Einstein never see her again. Well, of course, you know, that his parents' demand just made his love for Maleva even stronger. And it was a point of much contention within the Einstein family. And indeed, they became so close that they had a daughter before they became married, and the daughter was named Lezarel, and her existence was kept a very tight secret for more than the rest of Einstein's life. So only in the relatively recent past have historians discovered that the existence of this daughter, who unfortunately died at a very young age during, it's thought that she died during a scarlet fever epidemic. And we'll talk a bit more about that later. So Einstein is in a terrible situation. He can't get a job. He can't pursue a career in physics, which was his longtime goal. And he's sort of floundering to try to find out what direction he can pursue in his life. So after 2 years of fruitless job searching, the father of one of his friends, who had a lot of pull in the Swiss government, managed to arrange for a new job to be created in the patent office in the capital city of Bern. And he also managed that the job description for this new position was written in such a way that Einstein's lack of credentials would be sufficient for to fulfill the requirements of the job. In particular, Einstein did not have a PhD, and that would normally have been a requirement for this position at the patent office. Anyway, so with this political pull, Einstein is the shoe-in candidate for this job in the patent office, and he strides into the interview full of confidence and probably very overconfident, and it turns out that he fails the interview. So the patent examiner who conducted the interview deemed that Einstein was scientifically inadequate to fulfill the job at the patent office. Well, fortunately for humanity, political influence trumped the search for competent civil servants, and Einstein was hired as a patent clerk third class, even though he had failed the interview and been deemed technically unqualified for the position. Now, of course, that sort of political influence doesn't happen in our society today, but it apparently did back then. Okay, so he's got the job, patent clerk third class. It's sort of a entry-level minimum wage type of job, and it doesn't really pay enough so that he can marry Mileva and start a family and have legitimate children. So Einstein decides that in order to become eligible for a promotion to patent clerk second class, he should get a PhD. So he submits a PhD thesis to the University of Zurich. And in his PhD thesis, he goes through great lengths to explain why all the theories of the leading physicists of the day are really inane. And the reviewers of his PhD thesis, who were good friends of all the leading physicists of the day, decided to reject his PhD for whatever reasons, but the underlying reason is that he had offended the entire community with his PhD thesis. So his thesis is rejected, and that eliminates the possibility of a promotion and a higher paying job. And at this point, his father, Hermann Einstein, dies, which was very traumatic for Albert. And Hermann dies with not even a glimmer of the possibility that his son would ever become really successful in life. And Einstein greatly regretted for the rest of his life that his father never saw the chance that his son would become anything close to the immense success that he ultimately achieved. So one could say that Einstein did his best to place himself firmly on the road to failure and obscurity, and he did seem destined to fulfill the prophecies of his many detractors, including the headmaster at his elementary school, who said he would never amount to anything. But Einstein never gave up. Even though he had been rejected at every institute and university in Europe, even though his PhD was rejected, Einstein never gave up the goal of becoming a successful physicist. Now, let's talk for a minute about what was the status of physics in the year 1900 when Einstein was looking for a way to succeed. Newton had explained motion and gravity, and Maxwell and Faraday had explained electromagnetism, and that was as much as people knew about the nature at that time. So people were coming to the opinion that the study of physics was nearly complete, that we had the basic equations, we had all the equations that it would exist, and that we needed to measure a few things a little better here and there, but the study of physics had already succeeded in its most important objectives. And this was a general feeling that people had about science, not just physics. And in the same era, the commissioner of the US Patent Office has been quoted as saying that everything that can be invented has already been invented, which was amazingly absurd. but and it's not clear that he actually said it, but it's largely attributed to him. So there was this great feeling of accomplishment, and we're basically finished with science. And indeed, Lord Kelvin, who was the most famous physicist of the United Kingdom, was invited to give the keynote speech at the Royal Society in the centennial year 1900. And during his speech, he said that there is nothing new in science to be discovered, in particular, nothing new in physics. So there are, in this view, the view that most people had at that time, there weren't opportunities for a young bohemian rebel to come in and make a great discovery. The ground had been thoroughly scanned and turned over, and every rock had been examined, and there was nothing else to be discovered, according to the majority opinion. And indeed, the leading French mathematician and physicist Henri Poincaré said that there were only 3 little problems remaining in physics and in the year 1900. And he viewed these as sort of loose ends, not big deals, certainly not opportunities for dramatic discoveries. And these 3 little problems were Brownian motion, the photoelectric effect, and the inability that scientists had in trying to identify the ether. And we'll talk about each of these in much more detail later, but the key point for now is that the general belief of scientists at the time was that all the great discoveries had been made. There were these 3 little loose ends, and someone would eventually discover the not very important answers, and we would be done. So there really didn't seem to be much opportunity for a young emerging and yet unestablished scientist to contribute. Einstein, understanding this state of affairs of physics in the year 1900, decided his only chance of resurrecting his career hopes was to address these 3 little problems of Poincaré, and he determined that he would solve all of them. And in that way, he would finally turn his life around and move forward toward a successful career. Now, this is a picture of his home office in Bern, Switzerland, while he was a patent clerk. And of course, the picture on the wall wasn't hanging there back then. I've been to that office, and I've sat at that desk, and I put my hands on the table, and I tried to soak up any vibes that Einstein had left a century ago and see if I could somehow become a little bit smarter than I am. It didn't work, but it had been more successful for Einstein than for me. Anyway, later in life, Einstein was asked why he was the one that had made all these great discoveries and not others. And his reply was that it's not that I'm so smart, which isn't correct. But he continued, it's just that I stay with problems longer. In other words, he didn't quit. He was incredibly persistent. He could work on a problem night and day, almost 24 hours a day, for as long as 10 years. And even if he didn't see even a glimmer of success around the corner, he simply wouldn't quit. And because of this incredible determination, more than anything else, Einstein ended up solving some of the most fundamental problems in science. And in 1905, he had solved these three problems plus some other discoveries, and he published 5 spectacular scientific papers which revolutionized both science and physics in particular, and he solved in the process all of the 3 problems of Poincaré. So this is called Einstein's miracle year. And in fact, I don't know of any other scientist who has even published 2 such papers in the same year. So this was an incredible feat, and it would, in normal circumstances, have been spectacularly successful and guaranteed him a wonderful future all by itself. It's interesting to know why he was able to publish these papers at all. He had no PhD, he had no position at a major university or institute, he had no previous track record of successful discoveries, and yet his papers were published. And they were published on the decision of a single person, and that person, who was the editor-in-chief of the most famous scientific magazine of the day, the German journal Annalen der Physik, was Max Planck, and who later won the Nobel Prize. And Max Planck was probably the most famous physicist of the day, and he was editor of this major journal. And Max Planck read these papers that Einstein wrote, and he didn't think they were correct. He didn't accept the conclusions, but he did see some brilliant ideas in these papers. And on that basis alone, he ordered that these papers be published. And I think that wouldn't happen today. I think our procedures today are much more bureaucratic. Papers are peer reviewed. If these papers had been peer reviewed, they would have been rejected by every reviewer they would possibly have been sent to. So we have become, science has become more of an industry and more of a big business type of situation. And there is perhaps less opportunity now than there was 100 years ago for wild, crazy ideas to sneak into the papers and the journals and have all of the physics community given the opportunity to understand these wild, crazy ideas and decide whether they believed any of it or not. So the publication process is now more rigid and less flexible and less interested in people who don't have the union card to be part of the party. Einstein certainly didn't have the union card. So in these 5 papers, Einstein challenged the very foundations of physics itself. And he said that physicists, even after several centuries of since Newton published his laws, that physicists still didn't understand the basic mechanisms we use to measure weight or distance or time. I mean, these are very fundamental activities, and that we didn't understand the true nature of light or matter or motion. And really, if you take all these things away, there really isn't much left in physics besides this. I mean, everything we do in physics involves measuring these fundamental quantities and understanding, light and matter and motion. I mean, that's all that we have. So his papers challenged every existing theory that there was and every existing physicist that there was. And you can imagine that they weren't universally accepted. People didn't jump forward to accept these papers with open arms. This was a direct challenge to everyone's capabilities and intellect and integrity. This was very disruptive. And as a result, the papers were not accepted. The people didn't believe Einstein's work, even though he was later proved correct in all cases. So he published these incredible papers in 1905 as Miracle Year. And for one of those papers, perhaps the least controversial, he was awarded by the University of Zurich with a PhD, but still no one wanted to hire this guy. He was viewed as a menace. And for another 2 years, he continued to apply to universities and institutes, and he was continually rejected. Not even given an interview in almost all cases. And in 1905, sort of in a moment of desperation, he tried to become a high school physics teacher. He couldn't become a university physics teacher, so he tried to become a high school physics teacher, and he applied for an opening, and he was rejected as being unqualified to teach high school physics. So no one regarded this guy as, even competent, let alone brilliant. And finally, 4 years after his Miracle Year, 4 years of continued job searching, the man is now 30 years old, and he has failed at everything that he's tried to do to advance his career for basically every day for the last 30 years of his existence. And after that, he finally gets his first academic job, which is a junior professorship at the University of Zurich. And the only reason that he succeeded is he never quit. So that is a testimony to the importance of persistence. Persistence may well be the most important ingredient to success in almost every field of human endeavor. And Einstein's success is that due in largely to the fact that he never quit. He had more persistence than anyone else. Well, so in 1909, he gets the first job, and by 1913, he is a phenomenon. He is recognized throughout the physics community as being a brilliant young up-and-comer. Not so young, he's already 30. And Max Planck, who's the gentleman who published his first paper, said of Einstein in 1913 that there's hardly a major problem in physics to which Einstein has not made a remarkable contribution. I mean, you can't say something more wonderful than that about another physicist. And Einstein then received the best job in physics in the entire world, based largely on Max Planck's strong support. And that best job came in 3 parts. Firstly, he was appointed a full professor immediately at the University of Berlin, which was the most prestigious institution in physics at the time in the entire world, with the promise that he would never have to teach a class. Secondly, he was admitted to the Prussian Academy of Science with the promise that there would be no duties in that position. And thirdly, he was made the head of a new Institute of Physics, and he, with the promise that there would be no administrative duties in that position as well. So they gave him 3 jobs, 3 paychecks, and they told him he didn't have to do anything he didn't want to do. All he had to do was sit and think. I mean, what could be better than to get a job like that? And unfortunately, that position is no longer available. And he subsequently won, as we'll discuss later, the 1921 Nobel Prize in Physics. So the highlights of this career, to summarize, is that 1905 was his miracle year. He published 5 spectacular papers that revolutionized science. In 1909, he got his first job in physics, the junior professorship at Zurich. 1914, he got the best job in physics, a full professorship at the University of Berlin. In 1915, he published his most profound work, which is the theory of general relativity. And in 1919, when the theory of general relativity was confirmed, he became an instant worldwide celebrity. This was an era of the beginning of mass communication, worldwide communication, and he was one of the first icons of international celebrity. And he became the icon of science. Headlines in newspapers throughout the world heralded the confirmation of his theory of general relativity. And and he was then awarded the 1921 Nobel Prize for the photoelectric effect. And we'll talk more about that later. So any questions so far?
Yes. So what was his general response to World War I going on around him in the midst of his scientific pursuit? Is that recorded?
It is recorded. I don't recall any details, but he tried to avoid all political issues until World War II and the Nazis. That was a political issue he couldn't avoid. So he continued at the University of Berlin. Life became very difficult for everybody in Germany after the end of World War I. But Einstein still had his position, and he kept his position until Hitler came to power. So he continued to do physics at the University of Berlin after the war, and he's awarded the Nobel Prize after World War I ended. Probably a bit of an issue when he won the Nobel Prize was that the Nobel Committee wasn't that fond of Germans at the time.
Okay, thank you.
The confirmation of his theory of general relativity was done by a British scientist, Sir Arthur Eddington, and that was also involved with the controversy of the end of World War I. This was done in 1919. So here was a British scientist confirming the theory of a German scientist. And there was quite a bit of friction because of that. But Einstein tried to avoid getting involved in these things. He was against wars. He took the position that everyone should refuse the draft, that sort of thing. But he didn't have much clout until the Second World War. I mean, his celebrity began after the First World War.
Thanks.
So,
Thanks.
Did I answer your question, Andrew?
Yes, got it. Thank you.
Bert, can you hear me?
Is that you, Gil?
Yes. How are you?
Hi, Gil. How are you?
Fine. I
Good.
was interested. Do we know anything about the visual aspects of the patent office, where he spent all of his time around? In terms of, was it located near the train station where he's supposed to have come up with the ideas about velocity and movement and light.
Yes. The patent office was on the main square of the city of Bern, from which the train station is at one end. And it's important that Einstein was able to look out the window onto the main square. And one of the things that he thought of had to do, inspired him. One of the things that he saw, and because of the way he could put various disparate things together in his mind, one of the things that he saw inspired part of general relativity. And we'll talk about that when we get to general relativity. But he saw workmen on the roof of a building across the plaza, and he had the imagination to think of what would happen if one of them fell off, the seventh floor. And his conclusion was that as the person was falling, they would feel zero gravity. And that is the basis of the equivalence principle of general relativity. And it's a notion that probably no one had up to that point. Nowadays, we've seen astronauts in the International Space Station, and they're floating in the air, and we have some notion of that you can exist in a situation with zero gravity. But in Einstein's day, there was no such notion. and the realization that there was a frame of reference in which gravity was zero was a remarkable advance. It's sort of a bit of a gruesome thought, but it was a very important step forward for him. And I guess if there wasn't a window there, then he might not have had that idea. So he could look around. He got all of his patent work done in just a few hours a day, and that enabled him to work on his own theories as long as the boss didn't catch him. Okay, so let's talk about, excuse me, let's talk about his major discoveries and why they're important to us. So the first discovery I want to talk about is Einstein developed the means of proving definitively that atoms really did exist. And we're going to talk about that next week, so I'm just going to say a few words now. The existence of atoms had been debated scientifically for 25 centuries, and no one had come up with a decisive way of settling the debate. It had always remained an intellectual discussion with no data. Einstein provided a mechanism by which definitive data could actually be obtained, and other people did the experiment. Einstein never did an experiment in his life. And when the other people did the experiment that Einstein defined, they confirmed that, that atoms must exist in order to explain the results. So Einstein didn't prove that atoms exist, but he defined the path to prove it. And the next major discovery is his understanding of the photoelectric effect and the related photovoltaic effect. And those effects are important to us because they're the basis of the operation of solar cells, and also the CCDs, the charge-coupled devices that are the solid-state cameras that exist, these devices like this, that are the cameras that, the solid-state imaging devices that are the key element of the digital cameras that you might have, and also the key element of all modern telescopes. So modern telescopes no longer take images on conventional film. They use CCDs instead, which provide much greater resolution and precision. And the solar cells, are becoming a more and more important part of our economy. And this is the Hubble Space Telescope, which has a CCD imaging system in the telescope. The next of his discoveries is the theory that enables the construction of lasers. So once again, Einstein didn't make the first laser, but he provided the theory that indicated how a laser could be produced. And lasers are nearly ubiquitous in our society. They read our CDs and DVDs. They scan barcodes. They carry our telecommunications through fiber optic cables around the world. They're used in countless medical equipment and industrial equipment, and many other applications as well. Einstein's theories of relativity, both the special and general theory, are each critical to providing the proper operation of the global positioning system, the GPS. So the GPS navigation system that you probably have in your car results from a network of satellites that orbit the Earth that are continually emitting data, and the data analyzed properly defines your position on the surface of the Earth and the velocity with which you're moving. And if those data aren't corrected for Einstein's theories of relativity, the GPS system would have a cumulative error of 6 miles a day. So each day the error would be 6 miles worse than the day before. So if you got home on Monday night, you'd be in the wrong city by Tuesday night, and by the end of the week, you'd be out in the ocean. Einstein made major contributions to quantum mechanics, which is the underlying foundation of solid state physics. And that enables all of the microelectronics that we have, all of the digital circuitry that exists in our computers and our cell phones, and all of the other digital devices that we have throughout our society. Things that didn't exist 20 years ago or so, but nowadays seem to be, we can't live without. And finally, Einstein's most famous equation, E = mc squared, which we'll discuss for the rest of today, is the basis for it's the scientific basis for the development of nuclear weapons that ended the Second World War. It's the scientific basis for the development of nuclear power in all of the nuclear power plants that exist today, plus I hope in more advanced nuclear power plants, as we'll discuss, which would provide much smarter ways of producing energy. Ways of producing energy that would be free of pollution, would be very inexpensive, and would be unlimited in abundance. So these are all scientifically important discoveries, but also discoveries that have a tremendous impact on advancing our technological society. Economists estimate that perhaps 75% of the improvement in our economic power over the last century has been driven by science and engineering and the advance of technology. The other 25% is a return on capital investment. Despite all of these marvelous discoveries, there was one thing Einstein never did discover, and that was the comb. Well, he discovered many wonderful things, and as I say here, no one's perfect. So it would be wrong to think that everything Einstein said is correct. In fact, I would estimate that half of the papers he published were wrong. That doesn't sound good, but if you compare that to a major league baseball batter, a batting average of 500 would be spectacular. If you get on base half the time, that's you would be the MVP of the league for sure. On the other hand, if you're an airline pilot, a 500 batting average isn't nearly good enough. Everybody, 100% of the people want to get on the ground safe. So it depends what field you're in. And in theoretical physics, a 500 batting average is unheard ofly spectacular. If you look at all the theoretical papers that are published in physics, significantly less than 1% of them end up being correct. Less than 1%. To have a 500 batting average when you're trying to reveal new behaviors of nature, when you're trying to advance science, no one else has ever come close to matching that level of success. So even with half the papers being wrong, no one has ever matched the success of Einstein. And some of the times that he failed to be correct were his rejection of the concept of the Big Bang, which was originated by the Catholic priest Georges Lemaitre. His rejection of the notion of an expanding universe based on the equations of the Russian meteorologist Friedman, and his rejection of the notion that stars at the end of their lives collapse to these very small objects, neutron stars, white dwarfs, and black holes. He thought the notion of a black hole was so ugly that it couldn't possibly exist in nature because nature is fundamentally beautiful. That first theories of the collapse of dead stars is due to the Indian physicist Chandrasekhar. He also never accepted the full range of predictions of quantum mechanics, even though he had made one of the most essential contributions to launching quantum mechanics. He never accepted the full impact of his own work on quantum mechanics. And his claims of having achieved a unified field theory, which he published at least 2 versions of, those claims were also wrong. Einstein's rejection of the expansion of the universe was a result of his adopting a modification to his original equations of general relativity. He added something that's called the cosmological constant, which mathematically allowed the universe to be neither expanding nor contracting. It allowed the universe to exist in a stable configuration, which was the general belief of all Western scientists at the time, that the universe always was and always will be as we see it today. His original equations didn't allow a static universe, so Einstein added this cosmological constant in order to get a static universe, and that was mathematically incorrect, and it was, more importantly, contrary to what nature actually does. And when Edwin Hubble demonstrated that the universe was indeed expanding, Einstein called his cosmological constant the greatest blunder of his career. Okay, so these are the 6 major discoveries that I have identified. Other people may have a different list. And we are going to discuss all of these in this course. And today we're going to talk about his most famous equation, E equals mc squared. We're going to talk about atoms next week, the theory of special relativity in week 3, the theory of general relativity in weeks 4 and 5, and the lasers in week 6. And somewhere in there, we're going to talk about the photons as quantums of light. Okay, so here is the equation, E equals mc squared, and it establishes the equivalence of mass and energy, as we will discuss. This is probably the most famous equation in science. You may have seen it on coffee mugs and t-shirts, and despite the fact that everyone has seen this equation, probably everyone in the modern world has seen this equation. Despite that fact, there probably are relatively few people who would be comfortable explaining it to their children or grandchildren. And that's unfortunate because actually the equation is relatively simple, both as it's stated and also its meaning. And so I like to say, if you're capable of changing dollars into a foreign currency or vice versa, then you can understand Einstein's equation. So let's explore what this equation really means. So the E is for energy and the M is for mass, and we'll talk about c squared later. So let's talk about what mass is. It's basically how much material there is. So all normal matter, everything that we can see around us, all the people, all the planets, all the trees and the bugs and everything that we can see and touch, all of these things are made of normal matter, and all of that normal matter is made of a series of particles. You can think of all matter as being made of just 3 particles, protons, neutrons, and electrons. And the mass of an object is basically just a way to count how much of those particles are in each object, how many of those particles are in each object. So it tells you how much stuff an object has. Now, mass is sometimes confused with weight, and they are not the same thing. So mass is a property of the object itself, and weight is a combination of its mass and of the gravity that it experiences. So if you had a hammer that weighs 6 pounds on the surface of the Earth, it would only weigh 1 pound on the surface of the moon, because the moon is a smaller object than the Earth, and the moon has less gravity than the Earth. And if you were in the International Space Station where there is no gravity, the hammer would weigh 0. It would just float in space. But regardless of where you are, the mass of the hammer is always going to be exactly the same, because the hammer has a certain number of atoms and particles in it. And the mass is measuring the number of atoms and particles, and weight is measuring how that object is being attracted by gravity. And gravity is different in different places. In fact, there are no 2 places in the universe that have exactly the same gravity. And so weight is a number that's constantly changing for any given object, but mass never changes. Well, not never, but the mass is typically constant. So that's mass. It's relatively simple. Energy is a bit more complicated. I like to say that energy is the currency of existence. It's how we measure how much of something exists. So everything that exists has energy. And if it has twice as much energy, then there's twice as much stuff that exists. So it's another way of measuring the properties of the things around us. And one of the important aspects of energy is that the total amount of energy in the universe is always a conserved quantity. It's a number that never changes. So you cannot create more energy than exists at the moment, and you cannot reduce the number of energy, the amount of energy that exists in the moment. The amount of energy that exists in the universe today is exactly the same as the amount of energy that has always existed in the universe from the instant of the Big Bang until now. And all of these aspects make energy a very powerful concept in science. Energy has many forms, which adds to its complexity. So hot objects have more energy than cold objects. So heat is a form of energy. Objects at the top of a mountain have gravitational potential energy. Objects at the bottom of the valley have less gravitational potential energy. And a chemical energy is another form. So a gallon of gasoline has a certain amount of chemical potential energy. And we have learned how to take that potential energy and convert it into the kinetic energy of, for instance, a race car. So energy can be transformed from one type to another type, but the total amount will always remain the same. So what Einstein is saying is that mass is yet another form of energy. So we had heat and gravitational and chemical and kinetic, and Einstein, and there are many other forms. And Einstein is saying that mass itself is a form of energy. It's the most tangible form of energy. We can actually grab hold of it. Kinetic energy is the energy of motion, so it's not something that's really directly tangible, but mass is. And we can calculate how much energy any massive object has by using Einstein's equation. Now, I said his equation was no more complex than a foreign currency exchange. So if you have a bunch of dollars, excuse me, and you go to Japan, you're going to need to change your dollars into yen. And the procedure is rather simple. You take the number of dollars, you multiply by some exchange rate, and that tells you how many yen you're going to have. And Einstein's equation follows that logic exactly. If you have a massive object and you want to convert it into a different form of energy, such as heat, this is energy in the form of mass, this is energy in the form of heat. If you want to make that conversion, excuse me, then you take the amount of mass that you have, the m, you multiply by this exchange rate, c squared, and that will tell you how much energy you're going to have. Now, c is the speed of light. In conventional units, it's a very big number. In American units, the speed of light is 671 million miles per hour. Nothing moves through space faster than that. C squared is c times c, so that is a very, very big number. If we were in Europe, we would say that the speed of light is 1,080 million kilometers per hour. In different countries and different units, it would have a different number. But the point is, c squared is a very big number. And Einstein is saying that even a relatively modest amount of mass times this stupendously large exchange rate can produce a huge amount of energy. And indeed, if you take the energy in a single US penny, and if you converted that into useful work energy, which one day we will be able to do, you would be able to provide all the energy that 1 million people use in 24 hours in all the forms in which we use energy. So, and equivalently, the mass energy in a single US penny is equal to the amount of energy that we get now when we burn 2 million gallons of gasoline. So that penny has as much energy as 2 million gallons of burning gasoline. So you might think that you're paying too much for gas if a penny has the energy of 2 million gallons. Now, I happen to have an image of Einstein at the moment that he discovered this great equation. So he started off and he tried E equals ma squared, but that was too small. Then he tried E equals mb squared, but that was too big. And so he finally settled on the right answer, which is E equals mc squared. Now, before you start ripping me apart, I just want to say that this is what passes for humor among physicists. This is physics humor. Okay, this is more serious. This is an example of an interaction in elementary particle physics. This is a very famous picture. It is the discovery of a new particle called the omega minus. And the way this works is all the white area that you see is actually liquid hydrogen at very low temperature. A beam of particles comes in from the left. In this particular case, it's a beam of negative K mesons. One of the K mesons hits a proton in the nucleus of a hydrogen atom at this point, and it makes one particle that shoots off this way, which is a positively charged kaon, and the omega minus, which shoots off this way, and a neutral particle, a K0. The charged particles ionize the liquid and leave a trail of bubbles, but the neutral particles without an electric charge can't ionize the liquid. So there is, this K0 went from here to here, but you can't see it because it was neutral. But at this point, the K0 decayed into two particles that do have charge, and you see them. This omega minus decays into a lambda 0. Again, you can't see the lambda 0 because it's neutral. And it also decays into a K minus, which decays here. And anyway, this is a complicated process. But at this point, we are converting the kinetic energy of the K minus into mass energy of the omega minus. The omega weighs more than these two particles put together. So you had to convert the kinetic energy of the K minus to be able to produce this more massive object. And for instance, at this point, you have a massive K0 decaying into two pions that are much less massive. So now mass is being converted into kinetic energy. Here, kinetic energy is being converted into mass. And so you can analyze all of this with Einstein's equation, and that allows the physicists to figure out exactly which particles are doing what and prove that this was a brand new particle that had never been seen before.
Quick question.
Sure.
What causes the paths to diverge? They don't seem to diverge based upon their charge.
Yes, I should have said this. This is called a bubble chamber because of the trails of bubbles. The entire bubble chamber is embedded in a very strong magnetic field. So the magnetic field causes negative particles to bend clockwise and positive particles to bend counterclockwise. So we can tell the charge of the particle by which way it bends. You see, here's a positive proton that's bending clockwise and a negative pion that's bending counterclockwise. If I got the clockwise and counterclockwise correct.
Okay, thank you.
Sure. these particles have extremely high energy, and so they're bending very gradually, very slight bend, because the momentum is very high. The degree of bending enables us to measure the velocity of these particles.
So the K's, the plus and minus, they have less velocity than the.
Than the pions, for example. The
Okay.
Ks have a mass that's 500 in the right units, and the pions have a mass that's about 140. So they're much, they're 3 times less massive. So if they have the same energy, then this one has to be moving much faster.
Okay, thank you.
We have analyzed many millions of pictures like this, all the entire scientific community. Now, the same thing is going on at CERN, at the Large Hadron Collider. They have a different method of detecting the particle tracks. They don't use this liquid hydrogen. They have a much more digital way of measuring these things, and they collect many, many millions of events per second. So we used to collect 30 pictures a second, and now we probably are collecting 30 million events per second at CERN. So the technology has improved dramatically. This is really archaic by modern standards. Okay, so E equals mc squared explains how you convert mass into energy or energy into mass. Mass being a different form of energy than, for instance, heat and kinetic and so forth. And indeed, you can use this equation to understand the origin of all of the energy that we produce in useful work forms to support our society. All of the energy that we use ultimately boils down to mass being converted into energy at some point in the process. If you pour gasoline into your car and drive off, you are converting a certain amount of the mass of that gasoline into the energy that pushes the engine forward. The sun is a very efficient converter of mass into energy. All stars are, and our sun is converting 4 million tons of mass into energy every second. 4 million tons. And this yields the energy that makes the sun so bright and produces all of the light and the heat that radiates from the sun and ultimately supports all the life on Earth. So this equation explains the fundamental basis of energy. And let's take a practical example. In a past year, the total energy consumption of all Americans was equivalent to 25 trillion kilowatt hours. Now, not all of it was electrical, but if you convert different energy consumptions like gasoline into electrical units, then the sum of all that would be 25 trillion kilowatt hours. And that turns out to equal numerically the amount of energy that you would get if you converted 1 ton of mass, 2,000 pounds of mass, into useful work energy. So to support our energy requirements as in the United States, our job boils down to finding the best way to convert 1 ton of mass into the energy that we want. We want electricity. We also want to power our cars and trains and so forth. But we need a total of 1 ton of mass converted into energy per year to power our society. So I list here options to do that. If you burn coal, you need to burn 5 billion tons of coal. You will get 1 ton of useful work energy, and you will get 4,999,999,999 tons of toxic waste. It's not all actually toxic waste. Some of it is water, but nonetheless, most of it is stuff that you certainly don't want. It's greenhouse gases, it's toxic material. You got to dump this stuff somewhere. You're producing a huge amount of waste product, and you are being incredibly inefficient. You're getting 1 ton of energy and you're burning 5 billion tons. You've got to mine those 5 billion tons, and you've got to get rid of all of the waste product. So it's a terrible approach to producing energy. The next line is if you burn gasoline. This is a little bit better, but it's still terrible. You get 1 ton of energy and you get 2 billion minus 1 tons of waste. So it's a little bit better, but still awful. This is a existing nuclear power plant. Almost all of them are based on taking uranium and splitting uranium atoms. The atoms split into 2 smaller atoms, and a certain amount of mass is converted into energy. And the good news is that nuclear fission is 100,000 times more efficient than burning coal. So you get your 1 ton of energy and you're left with 49,999 tons of waste product. Unfortunately, the bad news is that waste product is radioactive to a large degree, and the disposal problems there are significant. But it's still 100,000 times better than burning coal. This is hydrogen fusion. This is where you take very small atoms, hydrogen atoms, and you merge them together to make a bigger atom. In this case, it would be helium. And it turns out that this is 40 million times more efficient than burning coal. And you can see it's 1,000 times more than 1,000 times better than fission. So you only need to burn, well, not 1,000 times, what is it? 400 times. You only need to burn 133 tons of hydrogen, and the oceans have a nearly limitless supply compared to that. You only need to burn 133 tons of hydrogen to get 1 ton of energy, and you get 132 tons of helium gas, which is a perfectly clean substance. So this is a process. This is what the sun does. We're not inventing something pie in the sky. This is how nature produces energy. So helium gas is perfectly clean. There is no radioactive waste. There is no toxic chemical that you have to dispose of. There is no greenhouse gas that you have to deal with. You get energy and you get helium gas. If you want to fill it balloons and party balloons and so forth with the helium, you can. If you don't want the helium, you just release it. It goes to the top of the atmosphere. It floats out into outer space. 24% of the universe is made of helium, so you're not even polluting outer space. And finally, an advanced society orbiting around a black hole can simply throw its trash into the black hole, and done properly, you can convert 100% of the mass of your trash into useful work energy. And I'm sure that any humanish society can generate plenty of trash. So this is the ultimate energy generating process. You need to have a convenient black hole handy, but not too close. but it can be 100% effective, and there's no residue whatsoever. Everything goes into the black hole and energy comes out. But that would be a little bit challenging. This is a much more reasonable goal. People have been working on this for 50 years, and success has always been 20 years around the corner. One hopes that eventually some genius will come along and figure out exactly how to do this, and society can enormously benefit from that. The problem is that this happens in stars all the time. The problem is that stars do that at temperatures of like 20 million degrees. And those are temperatures at which anything we might construct, any furnace we would build would melt. So we haven't figured out how to get that concentration of energy without destroying the apparatus. Okay, the other thing I want to say about this equation of Einstein's is that it's different in form from the typical physics equation. So the typical equation of physics is, for instance, this equation from Newton, F equals ma, F for force, m again is mass, and a is acceleration. Force, mass, and acceleration are three different concepts, and Newton is telling us how they relate to each other. This equation is energy and mass and a number. This is the speed of light squared, but that's just a number. It's not a variable. So you need that number because maybe you're not measuring mass and energy with the same units. If you did measure mass and energy in the appropriate units, then this would be 1, and it would just disappear from the equation. So this is saying that mass is energy. This is an identity. Mass is energy. This is not an identity. Mass times acceleration, both variables are equal to a third variable. So this is a relationship. This is an identity. This is telling you how you're related to your brothers and sisters. This is telling you that you are the same as your twin, if you will. Okay, that's the end of the heavy hitting today. So let's do something a little lighter. Let's talk about Einstein's two wives. Not at the same time. Well, yeah, actually they were at the same time. This is Einstein's first wife and Einstein's second wife. This is Mileva Merrick, and this is Elsa. Okay, so Mileva Merrick was Einstein's first life and his one true love. He met her at the Polytechnic. Her father was a Serbian general, and he had the unusual attitude in that day that women could be just as good as men in the university and just as good in science as the university. And he certainly thought his daughter would be. And being Serbian, they were Catholic, and she was the only woman in the Polytechnic, the college that Einstein and Mileva went to. She was excellent in math, and even better than Einstein, and she was excellent in physics. In classical physics, she was every bit as good as Einstein was. Einstein had these radical new ideas, and no one else in the world did, but Mileva could hold her own in any class in the school. She was born with a slight hip deformity, so she walked with a bit of a limp. And Einstein's parents rejected her because she was Serbian, not German, because she was Catholic, not Jewish, and because she had this hip deformity, and they didn't want to see any of that in their grandchildren. So they forbid him to see her, and of course that just made her all the more attractive. She was Einstein's intellectual peer. They would have extensive scientific discussions. And she is said to have aided in his 1905 papers. Her name does not appear on any of the papers, and there is no acknowledgement of her contribution in any of the papers, but it is widely believed that she helped Einstein with his background research and proofreading his papers to make sure that they were mathematically proper. So when the two of them were in college, they were penniless bohemian rebels, and it was them against the world, and they were madly in love with one another. And Mileva was the mother of all of Einstein's children. His first child, the Lazarev, the daughter, and his second and third children were boys, Edward and Hans second and Edward third. Lazarev is thought to have, because Lazarev was, Mileva got pregnant with Lazarev before they were married. She went back to Serbia to have the baby, and they kept it a secret to protect Einstein's reputation. In those days, it would have damaged his career prospects if people knew that he had a child out of wedlock. Well, so they were madly in love when neither one of them were famous, and neither one of them had any money. But when Einstein became famous, the doors that had slammed in his face all across Europe began to open, and some of the doors that opened probably shouldn't have. And Einstein had a whole series of affairs, one night stands with all of the ladies who wanted to be sleep with a bohemian physicist genius. Physicists were very popular in that age. And Einstein made no attempt to be discreet about his infidelities. Suffice it to say, his Nobel Prize was awarded for physics, not fidelity. Mileva naturally took this with great anger, and she was very upset that Einstein wasn't faithful to her. The relationship degraded, and they were barely on speaking terms. They lived together because they couldn't afford to live apart and because they had children. And one of the ladies Einstein had an affair with was named Elsa, who became ultimately his second wife. Elsa was a very different woman than Mileva. She was in no means a scientist. She had no interest in physics or science. All she wanted to do was cook and maintain a proper German house for a famous husband. So she wanted a famous husband that would give her the proper position in society. And one might unkindly say that Elsa weren't no Einstein. That would be both cruel and wrong, because Elsa's last name was Einstein. She was Albert's first cousin, both on the maternal and the paternal side of the family. They didn't have any children, so I guess that that issue didn't rise. She knew who she was marrying. He was unfaithful to his wife with her. So she knew that he wouldn't be faithful to her, and she was willing to overlook his many indiscretions as long as he always came home at night and as long as he was a famous scientist that could support her properly. So Einstein wanted to divorce Mileva and marry Elsa, and Elsa refused repeatedly to agree to a divorce. Divorces in Germany at the time had to be by mutual consent. So Einstein kept trying to convince her to divorce him, and she would not. And Einstein finally made a remarkable offer, financial offer. He said, for the rest of my life, I will give you half of my academic salary plus 100% of any income I make when I win the Nobel Prize. And he said, when I win the Nobel Prize, not if. He had no doubt that he was a genius and he would make remarkable contributions and he would be recognized with the Nobel Prize. So Mileva, being the math major that she was, she ran the numbers and she convinced herself that with half his salary and all of the Nobel Prize money, she would be able to support herself and her kids for the rest of her life. And indeed, she succeeded. So she accepted the offer. And when Einstein was awarded the Nobel Prize, and in 1922, when he got the equivalent in today's dollars of a $500,000 award, he gave the entirety of that award to Mileva. She bought with that 2 apartment houses in Zurich, and she supported herself and her children from the rents on those apartments pretty much for the rest of her life. Periodically, Einstein would add some money when one of their children, Eduardo, had a series of medical problems, and Einstein occasionally gave her more money to support that. But by and large, she lived the rest of her life without any further marriages or affairs, and supported her children. Now let's talk about the Nobel Prize Award. In 1921, the Royal Swedish Academy Committee, that is designated as to award Nobel Prizes. There is a committee for physics, a committee for the other categories. The physics committee was divided as to who should receive the award that year. So apparently there were a lot of people who were promoting Einstein and a lot of people who were very much opposed to Einstein receiving the Nobel Prize because his theories were so radical. Anyway, they couldn't come to an agreement, and so in 1921, there were no awards of Nobel Prizes in physics. The next year, the same committee got together, and they did come to an agreement this time. So they decided to award the 22 Nobel Prize to Niels Bohr, the Danish physicist, most prominently known for his contributions to quantum mechanics. And they awarded the 1921 Nobel Prize, which hadn't been awarded in that year. They awarded that to Albert Einstein. So it seems like there was a compromise. So the anti-Einstein faction was appeased by an award to Niels Bohr, and the pro-Einstein faction got the award to Einstein. So they both won the Nobel Prize in 1922, but the prizes for different years. But the Nobel Committee didn't stop there. They notified Einstein that he had been awarded the Nobel Prize, but they made it perfectly clear that the award was not for his work on relativity, which they deemed far too speculative to be recognized officially with the Nobel Prize. And they insisted that when he come to Stockholm and give his acceptance speech, he was not to mention this theories of relativity at all. There would be no talk of relativity in the acceptance speech. Well, Einstein wasn't pleased with all that, and he responded by telling him that he would be unable to attend that ceremony because he had previous engagements. Well, this is crazy. I mean, this is like the president-elect of the United States not showing up to be sworn in because he's getting his hair cut that day. I mean, this just never happens. When a scientist is awarded the Nobel Prize, they show up to accept. In any case, that was a bit of a snub as you can imagine, to the Nobel process. And the King of Sweden was disturbed by that. The Nobel Prize was relatively new, and it was a very prestigious thing that the Swedes were in charge of conducting. And so the King of Sweden sort of wanted to find a way to smooth all this over. He didn't want to overrule the Swedish Academy, but he didn't want to snub Einstein either. So he decided that he would throw a state dinner in Einstein's honor. And at that state dinner, he explicitly requested that Einstein explain his theory of relativity. Well, Einstein was not busy that day. So he gladly accepted the honor from the King of Sweden, and he gave a talk at the state dinner explaining his theory of relativity. So the summary of all of this is that the Royal Academy intentionally rejected the greatest scientific discovery in the last 200 years by not recognizing the theory of relativity. And instead, they ended up giving a Nobel Prize in physics to a Swedish engineer, Gustav Dalén, who invented a device to control the timing with which buoy lights flash. I have nothing against buoy lights, and it's important that they flash on time, but really that is not physics. Okay, so let's review what we talked about today. Einstein was the person of the century, deemed by Time magazine as the person that had made the greatest impact on human society during that entire century, saying he had the greatest mind and was the paramount icon of our age. This is a picture of Einstein's quote, laboratory. This is the most famous scientist in history, in my opinion. His name is second on the most recognized name worldwide list of all human beings. The number one, by the way, is Marilyn Monroe. And this famous scientist never did a legitimate experiment in his entire life. You don't think of scientists, you typically think of scientists doing experiments, but this was a pure theoretical physicist, one of the first to be entirely devoted to theory. And he would stare at that wall, which didn't have the poster, and he would have these amazing thoughts about how nature should work. And he was right about half the time, which was really remarkable. And just staring at that blank wall, he solved some of the greatest mysteries in the history of science. He took a very long time before people recognized his accomplishments and his capabilities. And indeed, for the first 30 years of his life, he failed at every attempt he made to further his career. He was rejected by every university in Europe. He was rejected by every scientific institution in Europe, but he never stopped trying to succeed. And because of this incredible persistence, he did eventually become the most famous scientist in history and the one that I believe has made the greatest contributions. These are the highlights of his career. 1905 is the miracle year in which he published these 5 spectacular papers. It took 4 years for him to get the first job offer. It took another 5 years before he rose to the top of the pack and got the best job in the entire world for physicists. And in 1915, he published his greatest contribution to science, its most profound contribution to science, the theory of general relativity. When the theory was confirmed in 1919, as we will talk about in week 4, Einstein became an instant worldwide celebrity. Everyone in the planet that was interested in science or interested in the affairs of society knew who Einstein was. He was one of the first international celebrities that emerged after worldwide communication enabled that. And he won the Nobel Prize for one of his lesser contributions, the discovery of the photoelectric effect. And that is the 1921 Nobel Prize, which he received in 1922. This is the list of 6 major discoveries that I will be discussing in this course. He proved that the basic property of light. He enabled the discovery of atoms, the proof of the discovery of atoms. His theory of special relativity and his theory of general relativity are his most prominent contributions to science. E equals mc squared, we talked about today, establishes the mass as a form of energy. And the last one on the list, which we'll talk about during week 6, is the theory that provides the foundation for the development of lasers. This is the comparison of converting dollars into yen versus converting mass into energy. It's the same procedure. You take an amount, multiply by an exchange rate, and you get the amount in a different form. So mass, a form of energy, times c squared gives you the amount of energy in some other form, such as heat or light. Okay, so those of you who are interested in reading as well as listening the material of the course, you may be interested in these books I've written. This is a general introduction to modern physics. It includes all of Einstein's work, plus cosmology, plus quantum mechanics, plus particle physics. And anyway, it's an accessible introduction. There is almost zero math in this book. And for those that like math, this is a definitive work on Einstein's theories of relativity. So every equation of relativity is derived. Every prediction of general relativity, I have listed every single step in the derivation of every prediction of Einstein. And you will not find that in any other book. All those derivations are very long. I have them in appendices. If you don't want to read them, fine. If you do want to read them, they're all there. Everything is there. And I wanted a single place where everything about relativity is discussed. So all of the paradoxes of special relativity are examined. I have advice on how to solve problems in special relativity in a sort of foolproof way. And I go through the entire derivation of curved space-time and all of the things that are required to understand general relativity. If you know nothing, you can start on page 1, and everything you need to know, I will explore with you. Same is true for this other book. If you've never taken a physics class, never taken a math class, you can still read this book and learn an enormous amount. Okay, we have some time for any last questions.
Robert, is there any thesis, this is Gil, is there any thesis that has been written somewhere about his Asperger's syndrome or the guess that he may have had that?
I read it in his biography by Walter Isaacson. The biography is, I forgot what the title is, but it's the biography of Albert Einstein. And Walter Isaacson was the editor of the New York Times for many years, I believe. So it's a very scholarly work, and it's full of references. I don't recall if he gives a specific medical reference for that or not. I don't know that a doctor would give a definitive diagnosis for somebody that's been dead for 50 years.
Right. I thought your analogy with regard to baseball was particularly wonderful in view of the times these days. You know the difference between baseball and politics?
What?
In baseball, you're out if you're caught stealing.
Whereas in politics, stealing is a prerequisite.
Whichever side you're on, doesn't matter.
Yes, I love it. We missed your jokes. Okay, any other questions?
So not directly related to this subject, but what kind of math background do you need to go through the Feynman Simplified series?
Oh, the Feynman Simplified.
Yeah, sorry about the curveball.
I shouldn't be surprised. I wrote the book. Yeah.
Right.
Week1 Simplified is a 4-volume book, and it's my translation into basic physics of one of the best physics course that's ever been presented at a college level. That physics course was presented by Richard Feynman, and I took the class, and he was, I took classes from Feynman while I was at Caltech. He was a friend of my dad's too, so I know him on several levels. He was an absolute genius and a wonderful guy, and at the foreword of the volume 1, he says his intention in writing this book is that no student in the class would understand 100% of it. So he wanted challenge, and there was no complication that Feynman saw that didn't delight him. So the book is full of very difficult and complex stuff. And you know, half of the students that took the class with me failed at Caltech.
Ooh.
So this is a super tough class, but the good news is he understood the material in the most profound possible way, and he had wonderful explanations for some very difficult things. So what I have done in my books is I've taken his wonderful explanations, and I have eliminated all of some of the most complex stuff that he deals with, which isn't germane to the main topic. And I reorganized it so that the presentation is more rational. He would sometimes start on one topic and then switch to a different topic and then switch to a different topic, and so on. So I tried to put all these things together in a logical sequence. And where he assumes that a person has great knowledge, I have explained the necessary steps. So I have made it possible for a dedicated college student to read Feynman.
So if you have just a calculus background, can you get through it?
Yes, it would be very challenging because the ideas are complex. But there's no better place to learn physics. I mean, he covers everything, and he makes you understand things in the most fundamental possible way. So if you really understand these things at a fundamental level, you don't have to memorize any equations. When the need comes, you can derive the equation. So, that's the kind of background that a professional physicist really needs. But it's a very challenging work. If you are interested, you might buy volume 1 and see what you think.
Okay, thank you.
Well, we might get together sometime, so I can help you more than that.
All right, thanks. I may need it.
Well, any book that you buy from me comes with a lifetime a license to send me questions.
Okay, super.
I try to answer all questions I get. That's questions that are well intentioned. There are some people I don't answer.
Okay.
Any other things we should talk about today? Okay, we are meeting again next week. We'll meet every Tuesday for the next 5 weeks, and that'll take us through the end of everything Einstein. So I thank you all for coming today, and hope to see you again next time. Goodbye.
Thank you.
You.
Thank